If your LLM pipeline needs retries, timeouts, and a human in the loop, a queue is usually not enough. You need a workflow engine that remembers where it was. This is the pattern you'll be able to implement by the end, which waits for human approval, then runs a language model job with explicit retries and a timeout. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Workflows save state. That is the core problem we solve here. When an LLM call fails or runs long, you want predictable retry behavior and a clear timeout. When a reviewer must approve content, you want the system to pause and then resume exactly where it left off, even if services crash. Temporal is a good fit because it is built to keep durable state and replay logic for distributed tasks. That durability makes retries and human gates reliable without glue code that breaks on restart. At a high level, think of a workflow as a living script. It steps through tasks, waits for signals, and records progress. You will see how to check the service, start a timed run, apply workflow-level retries, inspect activity heartbeats, and send a human approval signal. Each piece shows one common failure mode and how Temporal handles it for you. We will build a small example pipeline. It connects to a local temporal service to verify connectivity. Then, it starts a short LLM job with a hard timeout. Next, it demonstrates automatic retries for flaky tasks. After that, we watch heartbeats from a long activity. Finally, we send a human approval signal to unblock a paused review. No deep temporal internals are required to follow this. Now, we'll verify the connection to Temporal and read the server version. This snippet connects to a local temporal cluster and verifies it by reading the server version. It first creates a Temporal Python SDK client with client.connect halted at localhost 7233. The variable C holds the connected client, and I stores system information from service client getSystemInfo. The function connect returns both the client and the version string, so the global client can be reused in later steps. Asyncio.run executes the asynchronous connect coroutine and unpacks the tuple into client and ver. Finally, the print statement displays the connected version, so you can confirm the backend is reachable and healthy. The printed version proves the SDK is talking to a live temporal service. Next, we'll start a workflow with a run timeout, so a single job cannot run forever. This example starts an LLM job workflow with an explicit run timeout and returns its ID. The function run uses the previously created client to call start workflow, passing the workflow name LLM job and a short prompt input. It supplies ID to make runs easy to find, task queue to route work to your worker, and run timeout via datetime.tilde to bound total execution time. The variable h is a workflow handle returned by the SDK, and its ID property mirrors the provided identifier. Asyncio.run executes the coroutine and captures the handle's ID in WID. The printed started WFID confirms the job was accepted for execution within the timeout window. Now, we'll demonstrate workflow-level retries by running a flaky LLM task that may fail once. This code executes a flaky LLM job to demonstrate workflow-level retries in the Temporal Python SDK. The function run calls execute workflow with the workflow name LLM job flaky and a simple classification prompt. It sets retry policy to retry policy maximum attempts 2, which tells Temporal to automatically rerun the workflow once if it fails with a retryable error. The await returns the workflow's final result R after any retried attempts complete successfully. The code then returns len R so the print reflects a measurable outcome that depends on the eventual result. Increasing maximum attempts can improve resilience at the cost of longer tail latency. The printed classification length shows successful completion under retries. Next, we'll start a long LLM activity and inspect whether it is heartbeating to show progress. This snippet inspects heartbeats from a long LLM activity by describing the running workflow through the temporal service client. The function run starts LLM job long, which is assumed to heartbeat periodically while processing. It sleeps briefly with asyncio.sleep to allow the worker to begin executing the activity. Next, it calls service client, describe workflow execution with the namespace and workflow ID to retrieve runtime details, including pending activities. The expression len.d pending activities greater than 0 yields a Boolean flag indicating activity work is active and heartbeating data is likely present. Waiting longer increases the chance of observing heartbeats during slower tasks. The printed heartbeat seam confirms that progress signals are being recorded. Finally, we'll unblock a paused review by sending an approval signal from a reviewer. This example sends a human approval signal to unblock a paused LLM review workflow and waits for completion. The function run starts LLM review with a short publish request routed to the LLM task queue. It then calls hSignal with the signal name approve and a true value to represent a reviewer decision. After the workflow receives the signal and continues, hResult awaits and returns the final outcome string. Using signals for human-in-the-loop gates keeps the workflow durable across crashes and restarts, while preserving a clear audit trail. The printed final decision shows the review completed only after explicit human approval, validating the control point. This toy pipeline maps directly to a real review system. In production, the same pattern guards content publishing. The workflow persists state while waiting for reviewer action. Retries cover transient API failures. Timeouts bound runaway LLM calls. Heartbeats let operators see progress for long tasks. Recap. It is a durable workflow pattern that combines explicit timeouts, automatic retries, and human approval signals. Use it when you need reliable LLM jobs that survive crashes and require reviewer gates. One caveat: more retries increase completion time and can raise costs if LLM calls are expensive. Next step: tune the retry maximum attempts versus run timeout to balance cost, latency, and reliability for your workload. If short practical AI engineering helps, subscribe and watch the AI engineering videos.